Today we'll discuss two other very general AI methods of problem solving called means-ends analysis and problem reduction. Like generate and test, these two methods, means-ends analysis and problem reduction, are really useful for very well-formed problems. Not all problems are well-formed, but some problems are, and then these methods are very useful. These three methods, generate and test, means-ends analysis, problem reduction, together with semantic networks as a knowledge representation, form the basic unit of our fundamental topics in this course. We'll begin with the notion of state spaces, then talk about means-ends analysis. Then we'll illustrate means-ends analysis as a method for solving problems, and then we'll move on to the method of problem reduction. To understand the method of means-ends analysis, let us look at this blocks world problem. This is a very famous problem in AI. It has occurred again and again, and almost every textbook in AI has this problem. You're given a table on which there are three blocks, and A is on table, B is on table, and C is on A. This is the initial state. And you want to move these blocks to the goal state on this configuration so that C is on table, B is on C, A is on B. The problem looks very simple, doesn't it? Let's introduce a couple of constraints. You may move only one block at a time, so you can't pick both A and B together. And second, you may only move a block that has nothing on top of it. So you cannot move block A in this configuration because there is C on top of it. Let us also suppose that we're given some operators in this world. These operators essentially move some object to some location. For example, we could move C to the table, or C on to B, or C on to A. Not all the operators may be applicable in the current state. C already is on A, but in principle all of these operators are available. Given these operators, and this initial state and this goal state, write a sequence of operations that will move the blocks from the initial state to the goal state. Okay, David, what answer did you come up with?
So the first thing I did was I moved C to the table, then I moved B on top of C, and then I moved A on top of B. I don't think you can do it in less than 3 operators.
That's a good answer, David. That's a correct answer. Now the question becomes, how can we make an AI agent that would come up with a similar sequence of operations? In particular, how does the method of means-ends analysis work on this problem and come up with a particular sequence of operations? So we can imagine problem solving as occurring in a state space. Here is the initial state, here is the goal state, and the state space consists of all of those states that could be potentially produced from the initial state by iterative application of the various operators in this micro world. I want to come up with a path in this state space that takes me from the initial state to the goal state. Here is one path. This is not the only path, but this is one path to go from the initial state to the goal state. The question then becomes, how might an AI agent derive this path that may take it from the initial state to the goal state? Let us see how this notion of path finding applies to our blocks world problem. From the initial state, here is one path of going to the goal state. First, we put C on the table, then we put B on top of C, and then we put A on top of B, which is exactly the answer that David had given. This is one sequence, one path from the initial state to the goal state. The question then becomes, how does an AI method know what operation to select in a given state? Consider this state, for example. There are several operations possible here. One could put C on top of B or B on top of A. How does the AI agent know which operation to select at this particular state? One way of thinking about this is to talk in terms of differences. This chart illustrates the differences between different states and the goal state. So for example, if the current state was this one, then this red line illustrates the difference from the goal state. So we should pick an operator that will help reduce the difference between the current state and the goal state. So the reduction between the difference between the current state and the goal state is the end. The application of the operator is the means. That's why it's called the means-ends analysis. At any given state, I'm going to pick an operator that will help me reduce the difference between the current state and the goal state. Note, in a way, this problem is similar to the problem of path finding in robotics, where we have to design a robot that could go from one point to another point in some navigation space, from my office to your office, for example, if our offices were in the same building. There too we would use the notion of distances between offices. Here we're using the notion of distance in a metaphorical sense, in a figurative sense, not in a physical sense. So I'll sometimes use the word difference instead of distance, but it's the same idea. We are trying to reduce the distance or the difference, but in an abstract space. So going back to our example of going from this initial state to this goal state, I can look at the initial state and see that there are three differences between the initial state and the goal state. First, A is on table here, but A should be on B. B is on table here, but B should be on C. And third, C is on top of A here, but C should be on table there. So three differences. Here a number of operations are available to us, 9 operations in particular. Let us do a mean-sense analysis. We can apply an operator that will put C on table, in which case the difference between the new state and the goal state will be 2. We could apply an operator that will put C on top of B, that in that case the distance between the current state and the goal state will still be 3. Or we can apply the operator putting B on top of C, in which case the distance between the current state and the goal state will be 2. Notice the notion of reducing differences now leads to 2 possible choices. One could go with this state or with this one. Mean-sense analysis by itself does not help an AI agent decide between this course of action and that course of action. This is something that we'll return to both a little bit later in this lesson and even much more in detail when we come to planning in this course. For now, let us assume that we choose the top course of action just like David had done earlier. So this chart illustrates the path taken from the initial state to the goal state. And the important thing to notice here is that with each different move, the distance between the current state and the goal state is decreasing from 3 to 2 to 1 to 0. This is why mean-sense analysis comes up with this path, because at each time it reduces the difference. We can summarize the mean-sense analysis method like this. Compare the current state and the goal state. Find the differences between them. For each difference, look at what operators might be applicable. Select that operator that gets you closest to the goal state from the current state. We did this for the blocks and volts problem. We also did this for the guards and prisoners problem. We threw out those states in the guards and prisoners problem which were not getting us closer to the goal state. This is the mean-sense analysis method in summary. To understand more deeply the properties of means-ends analysis, let us look at another slightly more complicated example. In this example, there are 4 blocks instead of the 3 in the previous example, A, B, C, D. In the initial state, the blocks are arranged as shown here. The goal state is shown here on the right. The 4 blocks are arranged in a particular order. Now, if you compare the configuration of blocks on the left with the configuration of blocks on the right in the goal state, you can see there are 3 differences. First, A is on table, where A is on B here. B is on C, that's not a difference. C is on table, C is on D here, D is on B, D is on table here. So there are 3 differences. So this is a heuristic measure of the difference between the initial state and the goal state. Once again, we assume that the AI agent can move only 1 block at a time. Given this specification of the problem, what states are possible from the initial state? Please write down your answers in these boxes. So David, how did you fill up this table?
So it looks to me like the 3 things that we can actually do here legally are we can put D on A, we can put D on the table, or we can put A on D. So my first option reflects putting A up on D, and the other 3 things remain the same. My second option reflects putting D down on A, and the others remain the same. And my third is to put D on the table, and the others remain the same.
That's good, David. Okay, now for each of these states that is possible from the initial state, what are the differences as compared to the goal state? Please write down your answers in these boxes. What answers did you come up with, David?
So for the first one, if we put A up on D, we haven't accomplished any of the goals that we hadn't already accomplished, so our difference is still 3. Similarly, for putting D on A, our difference is also still 3 because we haven't accomplished anything new. However, if we put D down on the table, we've accomplished one of the goals we hadn't accomplished before, so there our difference is 2.
Good, David. So in each state, David is comparing the state with the goal state and finding differences between them. Given these three choices, which operation would mean-sense analysis choose? What was your answer, David?
So mean-sense analysis always chooses the state that most reduces the distance to the goal state. In this case, that would be the third option, because it reduces the distance down to 2.
That's correct, David. Given this current state, we can apply means-ends analysis iteratively. Now, if we apply means-ends analysis to this particular state, the number of choices here is very large, so I'll not go through all of them here. But I'd like you to write down the number of possible next states, as well as how many of those states reduce the difference to the goal, which is given here. What answers did you come up with, David?
So I counted out 7 possible next states. We can put B on A, B on D, B on the table, A on B, A on D, or D on B, or D on A. So that's 7 total operations. Of those, only one of them accomplishes a goal we hadn't already accomplished, and that's putting A up on B.
That's good, David. So the operation of putting A on B will bring us to this state. Given this state, we can again apply mean-sense analysis. Again, I am not showing all these states here, but I'd like you to find out how many possible states are there and how many of those states reduce the difference to the goal state. What answers did you come up with, David?
So I said here there are 3 possible next states. We can put A on the table, A on D, or D on A. The problem is that none of those states reduce the difference to the goal, and in fact, all 3 of those states move us further away from the goal. If we put D on A, then we no longer have D on the table. If we put A on the table or A on D, then we no longer have A on B. So with means-ends analysis, it doesn't look like there's any way to get any closer to our goal than we currently are.
That's right, David. And that means that mean-sense analysis does not always take us towards the goal. Sometimes it can take us away from the goal, and sometimes mean-sense analysis can get caught in loops. Mean-sense analysis, like generate and test, is an example of universal AI methods. These universal AI methods are applicable to very large classes of problems. However, they come with few guarantees of success, and they are often very costly. They're costly in terms of computational efficiency. They neither provide any guarantees of computational efficiency nor provide any guarantees of the optimality of the solution that they come up with. Their power lies in the fact that they can be applied to a very large class of problems. Later in this class, we'll discuss problem-solving methods, which are very specialized problem-solving methods. Those methods are applicable to a smaller class of problems. However, they are more tuned to those problems and often are more efficient and sometimes also provide guarantees about the optimality of the solution. Although means-ends analysis did not work very well for this problem, it in fact works quite well for many other problems, and therefore is an important AI method. Later in this class, when we come to planning, we will look at more powerful, specialized methods that can in fact address this class of problems quite well.
So how would you use means-ends analysis to solve Raven's progressive matrices? What exactly is our goal in this context? We might think of the goal in different ways. We might think of it as the goal is to solve the problem. Or in a different sense, we might think of the goal as to transform some frame into another frame and then trace back and find what the transformation was. In that context, how would you then measure distance? We notice that distance is important in doing means-ends analysis because it helps us decide what to do next. Once you have a measure of how to actually measure distance to your goal, what are the individual operators or moves that you can take to actually move closer to your goal, and how will you weight them to be able to decide what to do at any given time? In addition, what are the overall strengths of using means-ends analysis as a problem-solving approach in this context, and what are its limitations? Is it well suited for these problems, or are there perhaps other things that we could be doing that aren't necessarily under this topic that would actually make the problem even easier?
Let us now turn to the third problem-solving method under this topic, called problem reduction. The method of problem reduction actually is quite intuitive. I'm sure you use it all the time. Given a hard, complex problem, reduce it, decompose it into multiple easier, smaller, simpler problems. Consider, for example, computer programming or software design that I'm sure many of you do all the time. Given a hard problem to address, you decompose it into a series of smaller problems. How do I read the input? How do I process it? How do I write the output? That itself is a decomposition. In fact, one of the fundamental roles that knowledge plays is it tells you how to decompose a hard problem into simpler problems. Then, once you have solutions to these simpler, smaller problems, you can think about how do I compose those sub-solutions to the sub-problems into a solution to the problem as a whole. That's how problem reduction works. Let us start from where we left off when we finished mean-sense analysis. This was the current state, this was the goal state. As we saw from mean-sense analysis, achieving this goal state is not a very easy problem. However, we can think of this goal state as being composed of several sub-goals. So D on top of table, C on top of D, B on top of C, A on top of B, 4 sub-goals here. Now we can try to address this problem by looking at one sub-goal at a time. Let us suppose that we pick this sub-goal C on top of D. Given that sub-goal, we can now start from this current state and try to achieve this sub-goal. Now, of course, one might ask the question, why did we pick the goal C over D and not the goal B over C or the goal A over B? Well, one reason is that the difference between this state and that state had to do with C over D. But in general, problem reduction by itself does not tell us which sub-goal to attack first. That is a problem we'll address later when we come to planning. But now the major point is that we can decompose the goal into several sub-goals and attack one sub-goal at a time. Now that we have C over D as this sub-goal, we really don't care about whether A is on B or B is on C. What we are focused on is the other two states, C is on table, D is on table, because those are the blocks that occur in the goal state. So let us now see how mean-sense analysis may solve this sub-problem where we are worried only about the sub-goal C over D and D on table. So given this as a current state, what successor states are possible if we were to apply mean-sense analysis? Please fill in these boxes. David, how did you fill up these boxes?
So there are 3 possible moves here: A on the table, A on D, or D on A. So up top I have A on D, moving A to D. In the middle I have moving D up to A. And on the bottom I have A on the table.
That looks right, David. Let us now calculate the difference from each of the states to the goal state. What answers did you come up with, David?
So we haven't moved C, so C on D isn't going to be accomplished. In one of these 3 states, we did, however, move D, so that moves us away from our goal state. So mean-sense analysis would choose either of these 2 states.
So note that both the state at the top and the state at the bottom have an equal amount of difference compared to the goal state. We could have chosen either state to go further. For now, we're going to go with the one at the bottom. The reason, of course, is that if I put A on D, that will get in the way of solving the rest of the problem. For now, let us go with this state. Later on, we will see how an AI agent would decide that this is not a good path to take and this is a better path to take. So if we make the move that we had at the end of the last shot, we'll get this state. So now we need to go from this state to the goal state. Please write down what is the sequence of operators which might take us from the current state to the goal state. What sequence did you come up with, David?
So from this state, there are 7 possible moves we could make initially. Some of them are going to move us away from our goal state, so putting D on A or D on B are going to move us away from our goal state. To mean-sense analysis, the rest of the moves are relatively the same. Putting A on B doesn't get us closer, putting B on C doesn't get us closer, and putting B on D doesn't get us closer. However, we can see that we really need to get B out of the way of C to move it up here. Like Ashok mentioned, later on we'll talk about how an agent would decide that it needs to get B out of the way of C. But for right now, let's just go ahead and choose B on table as the next move. Given that, we now see that of the next possible states, only one reduces our difference, and that's to put C up on D.
That was the right answer, David. Thank you. You will note that we are leaving several questions unanswered for now, and that is fine. But you will also note that this problem reduction helps us make progress towards solving the problem. So the application of the last move in the previous shot will bring us to this state. In this state, the sub-goal C over D has been achieved. Now that we have achieved the first sub-goal, we can worry about how to achieve the other sub-goals. The other sub-goals, recall, were B over C and A over B. Given this as the current state and this as the goal state, please write down the sequence of operations that will take us from the current state to the goal state. What did you come up with, David?
So as before, there's actually two moves initially that will get us closer to our goal state. We could put A on B, or we could put B on C. We can recognize that B on C is the right goal because putting A on B will get in the way of putting B on C. And again, we'll talk about how we make that determination later. But for now, we'll first put B on C because that reduces our difference, and then we'll put A on top of B because that completes our trek to our goal state.
That was correct, David. Now this particular problem might look very simple because for you and me as humans, going from this state to this state is almost trivial. But notice how many different questions arose in trying to analyze this problem. Clearly, you and I as humans must be addressing these issues. This kind of AI analysis makes explicit what is usually tacit when humans solve this problem. And that is one of the powers of AI. Indeed, we have left a lot of questions unanswered, but each unanswered question then requires an answer. Now we know that we must develop methods that will somehow help address those questions. Like generate and test, and like mean-sense analysis, problem reduction is a universal method. It is applicable to a very large class of problems. Once again, problem reduction does not provide guarantees of success. Now that we have discussed mean-sense analysis and problem reduction, let's revisit one of the problems that we encountered when we were talking about the Raven's test of intelligence. So imagine that this is A and this is B. We can think of this as an initial state and this is a goal state. We know that A has been transformed into B. Now we can think in terms of a sequence of operations that will transform this initial state into the goal state. Here is one sequence. Delete the dot, then move the diamond outside the circle, then expand the diamond. Let us now see, we can think of this as an output of mean-sense analysis because each move here brings us a little closer to the goal state. The advantage of doing this analysis and coming up with a sequence of transformations that will take us from the initial state to the goal state is that we cannot think in terms of applying the same set of transformations to the image C. Let's do that. We'll apply one transformation at a time. So we'll apply delete, we delete the dot. Now we apply move to this state, and that can give rise to several states. We have shown two here. Both of these states fulfill the requirements of this move operation of taking the diamond outside the circle. And now for to each of these states, we can apply the operation of expand. Here we are expanding the circle, here too we are expanding the circle, but although by different amounts. Once again, the question here is what in the image A corresponds to what in image C. How do we know that the diamond inside here corresponds to the circle inside the triangle here? We'll discuss this in detail when we discuss analogical reasoning, but for now here is a partial answer. Remember that we had a semantic network representation of the image A, and in that representation we said that the diamond is inside the circle. Now we also have a semantic network representation of image C, and that semantic network representation says that the circle is inside the triangle. It is that inside relationship that hints that this circle must correspond to the diamond, because here the diamond is inside and here the circle is inside. So note then that the representation allows us to answer several questions about similarity, about correspondence. And when we have methods like mean-sense analysis, then we can do a systematic analysis of these transformations and try to transfer this set of transformations to the new problem.
What's interesting is we can also see this as an example of problem reduction. We initially just had a big problem that we had to solve, but here we've reduced it to 3 subgoals. Our first subgoal is to find the transformation between A and B. Our second subgoal is to transfer that transformation to C and find some candidate states for D. And our third subgoal would be to compare those candidate states for D to each of the choices in our problem.
That's good analysis, David. Let's go one step further. This also has generate and test in it. We are generating solutions that we can then test against the various choices that were given to us. So in this particular problem, you can see mean-sense analysis working, problem reduction working, and generate and test working. Often, Solving a complex problem requires a combination of AI techniques. At one point, one might use problem reduction. At another point, one might use generate and test. At a third point, one might use mean-sense analysis. Notice also that the one single knowledge representation of semantic network supports all three of these strategies. The coupling between the knowledge representation of semantic network and any of these three strategies, problem reduction, mean-sense analysis, or generate and test, is weak. Later on, we'll come across methods in which knowledge and the problem-solving method are closely coupled. The knowledge affords certain inferences, and inferences demand certain kinds of knowledge. This is why these methods are known as weak methods, because the coupling between these universal methods and the knowledge representation is weak.
So how would you apply problem reduction to Raven's progressive matrices? Before we actually talk about how our agents will do it, we can think of how we would do it. When we're solving a matrix, what are the smaller or easier problems that we're actually breaking it down into? How are we solving those smaller problems, and how are we then combining them into an answer to the problem as a whole? Once we know how we're doing it, how will your agent actually be able to do the same kind of reasoning process? How will it recognize when to split a problem into smaller problems? How will it solve those smaller problems? And how will it then combine those into an answer to the problem as a whole? During this process, think about what exactly is it that makes these smaller problems easier for your agent to answer than just answering the problem as a whole? And how does that actually help you solve these problems better? So let's wrap up what we've talked about today. We started off today by talking about state spaces, and we use those to frame our discussion of means-ends analysis. Means-ends analysis is a very general-purpose problem-solving method that allows us to look at our goal and try to continually move towards it. We then use means-ends analysis to try and address a couple of different kinds of problems, but when we did so, we hit an obstacle. To overcome that obstacle, we use problem reduction. We can use problem reduction in a lot of other problem-solving contexts, but here we use it specifically to overcome the obstacle we hit during means-ends analysis. Problem reduction occurs when we take a big, hard problem and reduce it into smaller, easier problems. By solving those smaller, easier problems, we solve the big, hard problem. Next time, we're going to talk about production systems, which are the last part of the fundamentals area of our course. But if you're particularly interested in what we've talked about today, you may wish to jump forward to logic and planning. Those will build specifically on the types of problems we talked about today. And in fact, in planning, we'll see a more robust way of solving the kinds of obstacles that we hit during our exercise with means-ends analysis earlier in this lesson.
Let us examine the connection between methods like mean-sense analysis and problem reduction on one hand and human cognition on the other. Methods like mean-sense analysis, problem reduction, and even generate and test are sometimes called weak methods. They are weak because they make only little use of knowledge. Later on, we'll look at strong methods that are knowledge intensive, that will demand a lot of knowledge. The good thing about those knowledge intensive methods is that they will actually use knowledge about the world to come up with good solutions in an efficient manner. On the other hand, those knowledge intensive methods require knowledge, which is not always available. So humans, when they are working in a domain, in a world at which they are experts, tend to use those knowledge intensive methods because they know a lot about the world. But of course, you and I constantly work in worlds and domains in which we are not experts. When we are not expert in a domain that might be unfamiliar to us, then we might well go with methods that are weak because they don't require a lot of knowledge. We're at the end of this lesson. Please summarize what you learned in this lesson inside this box. And thank you for doing it.